Hey everyone. So welcome back. This is Avery again. It seems like I've become the person who's making all the videos. John just asked me to add an extra example problem for the synchronization project. So in addition to the walkthrough, you also have this example problem. This problem used to be on the CS140p set. So previously it was the Caltrain problem followed by the chemical reaction problem. But then, I guess John recently decided to swap the chemical reaction problem for the party problem, which is the one that you're doing. So instead, chemical reaction is just going to be an example that we're going to do right now. If you haven't already started on project 3, hopefully this is helpful, shows you an example of how you use mutexes and condition variables. While if you already finished the project, then great job. This video should hopefully still be useful when you are studying for the midterm. Right, midterm's coming up in 2.5 weeks, and you can bet that there's going to be some synchronization problem. All right, so let's take a look at this problem. This problem is called chemical reaction, and it's all about making water. So it takes 2 hydrogen atoms and 1 oxygen atom to make water. And just like the PSET problems, each atom here is going to be represented by a thread, right? It's like a train is represented by a thread, a passenger is represented by a thread. Here, the atom represents a thread. And there are 2 different kinds of atoms. One is the hydrogen atom. The hydrogen atom, that thread will invoke reaction _H, and the oxygen atoms are going to invoke reaction _O. Okay, and we're going to write both of these functions. So these functions have to synchronize in a special way, where these functions have to delay until there are 2 hydrogen threads and 1 oxygen thread that have entered their respective functions. Okay, and then once that happens, exactly one of the functions is going to call make water. Okay, it's a function that you're given. After make water is called, then these 3 threads are allowed to finish their respective functions. So when you go through this problem, I like to think about what the synchronization points are in this problem, right? What threads have to be waiting for other threads? And here, you should notice that there are 2 points of synchronization. I recommend you pause the video, try to identify what the 2 points are. So pause the video right now. Okay, cool. So hopefully you've identified what the synchronization points are. The 2 points are, notice here, we have to first delay until there are at least 2 hydrogen threads and 1 oxygen thread present. Okay, so there is some waiting going on where we have to make sure that the correct threads are there, or they have entered the function and they're all ready to go. Okay, then one of the threads is called make water. And then there's another synchronization point here where these functions can't complete until they know for sure that make water was called. So imagine the 2 other threads who are not calling make water. They have nothing to do, but they can't return. They have to wait until the 3rd thread has finished calling make water. Okay, so now that we have the synchronization out of the way, let's take a look at the code. So here's an example, just to show you an example of how everything runs. So here is a test case that I wrote. You have here we launch a hydrogen thread with index 0, hydrogen thread index 1, oxygen thread index 0. And then because the 2 hydrogen threads and the 1 oxygen thread have entered the function and are ready, we call make water. Okay, now once make water is done, then these threads can finish, right? The oxygen thread finishes, hydrogen thread finishes, hydrogen thread finishes. So what's important is that you have to make water can only be called after the 3 threads are ready. And these 3 threads can only finish after make water is done. Okay, and you can see something similar going on right here. So this is done, but then now there are more threads going on. An oxygen thread has entered, a hydrogen thread has entered, and an oxygen thread has entered. Notice that we have 2 oxygen but 1 hydrogen, so that can't make water. So notice that no water is made. They have to wait until another hydrogen comes, and then we notice that we can successfully make water. Only after the water is made are the 1 oxygen thread and the 2 hydrogen threads going to finish. Okay, now the order in which you pick the oxygen, right? There's 2 oxygens. Whichever oxygen you pick, it doesn't really matter. Here it just picks oxygen 1. So notice at the end of this, notice that there's 1 oxygen still remaining there. Okay, so when you launch 2 more hydrogen threads, water gets made, and those 3 threads are able to finish. Okay, so that's this test case. I'll test the code so you can play around with the code a little. That's the starter code that I have here. I wrote this as a simple test harness, but yeah, you can take a look. I have the functions that launch the oxygens and the hydrogens. Okay, cool. So let's take a look at the reaction.cc. This resembles what you did on what you will do on project 3, right? You're given a class declaration up here, and then you're given the implementations down here that you have to fill out. So you can see that there's a constructor, and there are the 2 functions that you have to write. You're also already given a single mutex, right? Remember that we are doing the monitor style, so that you only need 1 mutex. That single mutex will protect all the variables in your reaction. Give me 1 second. I have to find a charger. All right, and we're back. I found a charger and we will not run out of power. So yeah, back to the mutex. Yes, the single mutex needs to protect all the members. All right, so let's try to imagine what our code needs what needs to happen for each of our 2 functions. Well, I think to make this easier, let's go to the iPad and I'll draw some pictures. Switch it over here. All right, so when we do these synchronization problems, I like to personify these threads. Right? I like to pretend I am one of these threads and think about what I will do, right? Who am I waiting on? And when do I have to tell someone that I'm ready to go? And out of these 3 atoms that have to react together, I think the oxygen one is most interesting, right? And I feel like that is the easiest to get started on, because if we think about the hydrogen thread, we have to imagine there's 2 at a time. But for the oxygen thread, we know there's 1. And because of that, I feel like it's easier if the oxygen thread is the one responsible for calling make water, right? There's 1 oxygen thread and make water needs to be called once. So let's think about from the perspective of the oxygen thread. Okay, that's the one that we're going to have create water. And I'm going to treat the oxygen thread like the conductor, right? The oxygen thread is responsible for orchestrating everything. It's going to call make water, so it has to appropriately make sure everyone is ready, and it has to make sure that everyone knows we're done. We can exit the function. All right, let's think about what we have to do for the oxygen thread. Well, first we have to enter the function, right? Enter reaction. Oh, okay, now what's the next step? What does the oxygen thread need to do? It's definitely going to call make water. But before it calls make water, it has to do one important step. And that step is to wait until that's very big, until there are 2 hydrogen threads ready. Right? Yeah, because we know that's the oxygen thread. It needs to know there are 2 separate hydrogen threads that are ready. Okay, then after it calls make water, then it can successfully exit reaction. Oh. Let's now think about from the perspective of the hydrogen threads. They're going to enter reaction H. Now, what happens when these hydrogen threads enter reaction H? Well, these hydrogen threads, they're not going to do anything, right? They're just going to wait. Once they arrive, they're just going to wait until oxygen has called make water, and then they can exit. But how is oxygen going to know that the hydrogen threads have arrived? Right? The oxygen thread is just there, just waiting until the hydrogen threads have arrived. Okay, so we need some way for the hydrogen threads to tell the oxygen thread, hey, we've arrived. Okay, and then the way to do that is we can have a shared variable, right? A variable that counts how many hydrogen threads have arrived. And then this oxygen thread can then just be waiting and waiting until the number of hydrogen threads that have arrived is at least 2. Let's add a variable called num hydrogen equals 1 equals 1. And then in our wait condition, we can change this to wait until num hydrogen is at least 2. Okay. Now, what do the hydrogen threads need to do next? Well, the hydrogen thread, after it has incremented num hydrogen by 1, so oxygen thread knows that a new hydrogen thread has arrived. Now the hydrogen threads just need to wait until make water is done. And then it can exit. Okay. All right, let's try implementing this. So switching screens again. All right, so we are back to the code. So let's try to implement that pseudocode we just wrote. All right, so here in the reaction H, what we're going to do is we're going to increment our variable called num hydrogen. We're going to increment that by 1. And then we're just going to wait until make water is done before we exit the function again. All right, while for the oxygen thread, after it enters the reaction underscore O, it needs to wait until num hydrogen is greater than or equal to 2. Then it calls make water before it can finish. Okay. And then, so let's try to see what small missing pieces we need. We have this num hydrogen variable, and it's a variable that we need to share across all the instances of all threads that are calling reaction H and reaction O. So let's just declare that as a variable here. We're going to declare that called num hydrogen. And because it's a member variable, we're going to initialize it in our initializer list. Initialize that to 0. Okay. Notice that this variable is not static. We need to share this variable across all the threads that are using this single reaction, but we can create multiple copies of this reaction, and they should each store their number of hydrogen separately, right? Imagine you have different places where different reactions are happening. Okay. So here we don't use static, we just use a simple member variable. All right, now we have added our variable, and we are going to increment 1 up here. And down here, I forgot to write it inside the pseudocode. Don't forget that once you have waited until there are 2 hydrogen atoms, before you call make water, you have to decrease this by 2, right? Otherwise, you're never really consuming the hydrogen atoms, and these oxygen atoms are just going to consume more and more hydrogen atoms. All right, so now that we have that going, this currently presents an issue where we have different threads who are simultaneously accessing num hydrogen. And when you have multiple threads trying to change the same variable, that's where race conditions come in, right? It depends on which variable gets there first. The value of the variable might change depending on which thread gets there first. So to prevent issues like that happening, that's where this mutex comes in, right? Mutex allows us to create critical regions so that only one thread is able to be within all these critical regions at any point. Okay, only one thread is able to enter that critical region. Okay, and how we typically do that is we use this thing called a unique lock. So let's call it lock. And what this unique lock should do is it should acquire the mutex, which we do using that. And by creating this object, what happens is that the constructor of this unique lock takes M and locks it. Okay. And then when this object goes out of scope, it then unlocks it. We don't have to explicitly call lock and unlock. This unique lock does it for us. You might be wondering, why do we need that? Why can't I just make my life easy, call lock myself, call unlock myself? Yeah, so this is actually a concept in C++ called RAII. You can read more about it if you just Google RAII. But the key idea here is that locking something in the constructor and then releasing it in the destructor makes it much easier to write, because then if we have a lot of if statements, like if something and return else, maybe more code, maybe more else ifs. Okay, if we have code that looks like this that are messy, there's a lot of different control flow paths, then it's very cumbersome to have to write, mlock here, munlock here. Wait, but if we go into here, then it's going to return skipping over the unlock. So we have to write an extra mlock here. And you just have to go through all the different cases and make sure that you have unlocked before you return from the function in every possible case. Right? And then when you add exceptions to this gets very messy. You have to check so many different cases. It's just way better style, way easier to get everything right if you use a unique lock, because whenever this object goes out of scope, M is automatically unlocked. No matter which way you exit this function, it will always get unlocked. Okay, that's called RAII. It's one of the cool concepts in C++. I recommend that you search it up. All right, so now we have this unique lock. Now we can safely modify num hydrogen. And similarly for the reaction O, we should acquire the lock here so that when we modify num hydrogen, we will not be, there will not be race conditions on this variable. Okay, cool. So yeah, now we have it almost done. Now we just have to implement this while loop. So before you have learned about condition variables, the very natural way to implement this is to say while num hydrogen is greater than or equal to 2, and then just do a spin lock, right? Just literally do nothing. Okay, this is what we call a spin lock. And as you saw in lecture, this is used sometimes for multi-core machines, but this is generally not super efficient, right? The CPU is just running in this while loop without just constantly checking the condition again and again without really doing any work. So you learned in section that a more efficient alternative is to change this into a condition variable, right? Oh, I guess you have to do m.unlock, m.lock. Do something like this so that you're able to continuously unlock and lock this lock so that other threads are able to modify num hydrogen. Okay, but that is pretty cumbersome. So instead, a more efficient approach is to use condition variables here, right? Whenever you have this while loop that resembles like a spin lock, where you're constantly just waiting for a condition to happen, it's much better to have this thread go to sleep. So what we're going to do is we're going to add a condition variable. So how do you add that? You add that here, condition variable. And let's call this, this is waiting until the hydrogens are wetting. So let's call this wait for hydrogen. Okay, I'm going to initialize this in my initializer list as well. Remember, always use the initializer list. Don't try to assign these members one by one. That's a common source of weird compiler errors. Okay, so now that we have wait for hydrogen, instead of calling this weird unlock and lock loop, we can just say wait for hydrogen. That's our condition variable. We're going to pass in, we're going to call the wait function. Now the wait function, remember what the wait function does. It does 3 things atomically. It will release the lock. Right? It needs to release the lock so that other threads are able to modify the condition. And then when it gets signaled or when it gets notified, it will wake up and it is able to then check, acquire the lock so that it can go in the while loop and check the condition again. So here you always pass in the unique lock here, lock. Okay, so by doing this, even though we still have a while loop, this is no longer a spin lock, because when wait is executed, the thread goes to sleep until someone else wakes it up. Okay, so this line of pseudocode is done. Now, it seems like our reaction function is almost done. But the issue is when the reaction thread goes to sleep, right? When the oxygen thread goes to sleep, how is it going to know when to wake up? Right? Someone has to notify it to wake up. So here, for condition variables, you always have the thread who might have changed the condition to notify the threads that are waiting. So here in reaction, we want to notify this oxygen thread that I might have modified the num hydrogen condition. So you should wake up and check again. So after I do the num hydrogen +1, here's where you should do wait for hydrogen, notify 1. We only notify 1 here because we are, there's only going to be one oxygen atom that is going to be that can react with this hydrogen. So we just need to notify one of the threads. All right. So there a common question that we often get here is, you're still holding the lock. Is it okay to call notify? And yeah, that's totally fine. As you'll implement in project 4, when you call notify, the threads that get woken up, they don't immediately start running. Instead, they get scheduled. So the threads that are scheduled, they may or may not. Well, if they try to acquire the lock again, it does not really matter. They'll just continue blocking until this lock has been released. Okay, so it's totally fine to still be holding the lock when you call notify 1. The thread that was waiting will still get woken up later. Okay, so we're almost done. We have implemented this condition. Now, the only thing that's remaining is this wait until make water is done, right? We still haven't really implemented this condition. And you might try to think, okay, how might I implement that, right? Do I do like some sort of while loop, like while make water is done, maybe some Boolean, right? Maybe we can add a Boolean variable here, okay? And while that is possible, we could implement it like that. There's actually a simpler way to implement this. Okay, what we're going to do here is we're going to add a condition variable here called wait for make water. Okay, and here I'm going to have these just call wait for water dot wait. And remember, you always pass in the lock. You don't pass in M, you pass in the unique lock. Okay, so now we are waiting until make water is ready. Then remember, when you have threads that are going to sleep, you need someone to wake them up. Who's going to wake them up? Well, the reaction O is going to wake them up. And I'm just going to have them wake them up like this. Wait for water dot notify 1. And because there are 2 hydrogen threads that are waiting for you, you should call it twice. Okay, that makes sure that there are 2 hydrogen threads that have reached this point, they get woken up. And now you might be wondering, wait, can't you have some, can you have some weird issue? Is it possible for the reaction threads, the hydrogen threads to not have reached the wait condition, and then you sort of call the notify ones too early, right? This is a common conceptual question about condition variables, right? If you have a thread that is waiting, or rather, if you have a thread that signals, but there are no threads that are waiting, then that signal doesn't do anything. Even if a thread comes in later and calls wait, it's still going to wait, keep waiting until someone new comes in and calls signal, right? If you call signal and there's no threads waiting, nothing happens. So a common concern is then, what if reaction H is a little slow? It has not reached the wait, but then reaction O calls notify 1. Okay, I want you to pause the video, try to trace through that problem, right? Is it possible for the oxygen thread to hit this notify 1 before the reaction threads are able to call wait? Sorry, the hydrogen threads are able to call wait. Give you a moment, try to think through that. Yeah, and the answer to that is no, because what happens here is that, remember, this lock creates a critical region inside this function, and only one thread is able to run in that region at a time. Okay, so you're guaranteed that if you acquire the lock and you're running this region, then no other hydrogen threads or oxygen threads are going to be able to run their function until you release the lock. Okay, so when the hydrogen thread acquires a lock, it's going to continually run until it hits the wait. Okay, So if a hydrogen thread is able to start the function and acquire the lock, then it will keep running until it hits the wait. For the oxygen threads, they can only run when they acquire the lock. And notice what has to happen for them to reach this point, right? They have to have already waited until the hydrogens are ready. That implies that the hydrogen threads have called notify one already. Okay, so the sequence of events has to be the hydrogen threads call notify one, and then they call wait. Then the oxygen thread gets access to it and it wakes up from wait before it's able to call make water and then notify one. So we're actually guaranteed that notify one will be called only after the two hydrogen threads that are involved in the reaction have called wait. Okay, yeah, it's a tricky conceptual question. If that didn't quite make sense to you, I recommend that you rewatch the last couple minutes and just make sure you understand that concept. Condition variables themselves do not remember how many times signal has been called. Okay, it's not like the pendulum problem from section. The reason why this works here is because we're guaranteed, because we're acquiring this lock, we're guaranteed that wait, the hydrogen threads will always reach wait, so that there are always going to be hydrogen threads that are waiting by the time the oxygen thread finishes make water and calls notify one. Okay, now think about that. That same trick will not work for this initial while loop. And as an exercise, I recommend you try figuring it out. Why do we need a while loop here, but why do we not need a while loop down here? Okay. All right. So yeah, we've basically implemented our function. I don't think there's anything left to. Oh, we need to initialize this. All right, and that's mostly it. Let's just double check that this code works. I'll post the instructions for how to compile this. I don't have a make file for this, so I'm just gonna. Ooh, that is a lot of errors. Oh, okay. Yes. Don't forget to always type standard mutex. Okay, and then you can check test it out. Reaction. It's launching the threads one by one. And I added a little delay in there so you can just ensure that the make water is called correctly. No, make water is not called correctly. Let's see what the issue is. All right, so I think I figured out the issue. There was a little typo over here. So remember, the while loop here is saying when should the thread keep waiting, right? It's not when should the thread continue, it's when should the thread keep waiting. So this condition over here should not be when number of hydrogen is greater than or equal to 2. That's the condition when we do want the thread to stop waiting and continue to make water. So we actually want the negation of this. We want to say while the number of threads is less than 2, then keep running and then keep waiting. Once it's no longer less than 2, then we can continue. Okay, so let's just double check whether that solves the issue. Compile. Cool, and then you can see that indeed solves the issue. Right, the water gets successfully made, and yeah, our code works. Okay, so yeah, this is the reaction problem. This starter code and the test harness and the starter code will be available for you to implement, and I recommend that you try this problem out. This is a pretty typical exam problem, so I recommend that you carefully review this problem, carefully review all the tricky conceptual questions that I asked in the middle. And if you have any follow-up questions, feel free to ask on Ed, and I'll try to answer them. Okay, otherwise, good luck on project 3, and I'll see you in the next video for project 4. Bye.